Hello students, in previous lecture we have studied about the dissociation constant of weak acid, that is Ka, and dissociation constant of weak base, that is Kb. Then we have already studied the different theories or concepts of acid and base, that is Arrhenius theory of acid and base, Lewis theory of acid and base, and Bronsted-Lowry theory of acid and base. Then Arrhenius concept of acid and base, which can be expressed quantitatively by one more concept, that is Oswald's dilution law. And Oswald dilution law, it is applicable to only weak electrolytes. Therefore, today we are going to study about the Oswald's dilution law for weak acid as well as Oswald dilution law for weak base. Then this Oswald dilution law shows the relationship between dissociation constant of acid, that is Ka, and degree of dissociation of that weak acid, as well as it shows the relationship between, that is dissociation constant of acid, degree of dissociation, and concentration as well as dilution of that substance in aqueous medium. Today we are going to discussing on about that is Oswald's dilution law for weak acid and Oswald dilution law for weak base. Now I am going to discussing with you the new concept, that is Oswald's dilution law. Then see here, Ostwald's dilution law. This law is applicable to any weak acid as well as weak base. Arrhenius concept of acid and base, which is expressed quantitatively by Oswald dilution law. Therefore, first of all, we will discussing on the Oswald dilution law for weak acid. Then see here the derivation for dissociation constant and degree of dissociation of weak acid. Then that means here Oswald dilution law, it express the relationship between dissociation constant of weak acid, that is Ka, and degree of dissociation of weak acid, that is alpha. That means here the derivation which is related with Ka and alpha of weak acid. First of all, see here, let us consider the weak acid HA, that is HA is a weak acid here, which in aqueous medium dissociate to gives H plus ion and A minus ions. That means here that weak acid HA dissociate to gives H plus or H3O plus ion, that is hydronium ion, and A minus ion. Then see here, let us consider total at initially 1 mole of HA dissolved in given amount of excess amount of water and in VDM cube of solution. That means 1 mole of HA, that is weak acid, dissolved in VDM cube of, that means here 1 mole of HA, that is weak acid, dissolved in VDM cube of solution, and at equilibrium, that means after some time equilibrium is attained in dissociated ions and unionized HA molecule, that is weak acid molecule. When equilibrium is attained, out of 1 mole, only alpha moles of HA, weak acid, undergoes dissociated. Therefore, first of all, we have to write the equation or ionic equilibria for acid. See here, HA in aqueous medium, it dissociate to gives H3O plus A minus ion. And see here, at initially total 1 mole of HA are there. That means 1 mole of weak acid is there at initially, at start. Then H3O plus ions and A minus ions are 0. As dissociation gets started or dissociation takes place, the H3O plus ions and A minus ions formation takes place. And the stage comes when equilibrium is attained between dissociated ions and, that is, unionized HA molecule. And when equilibrium is attained, at equilibrium, then alpha moles of HA, when alpha moles of HA dissociate to gives alpha moles of H plus ion and alpha moles of A minus ions. That means here, suppose 0.2 moles of HA dissociates, it gives 0.2 moles of H plus ion and 0.2 moles of A minus ions. Therefore, here alpha moles of HA undergoes dissociation at equilibrium. Therefore, at equilibrium, H3O plus ions are alpha and A minus ions are also alpha. And here at equilibrium, the remaining molecules of HA is, at initially it is 1 mole. Out of that, alpha moles undergoes dissociation. Therefore, 1 minus alpha. That means here, out of 10 moles, when 8 moles undergoes dissociation, then 10 minus 8 moles of acid remains as it is. Similarly, 1 minus alpha moles remains as unionized molecules of weak acid. And therefore, we can write the concentration terms, concentrations in mole per dm cube, mole per liter. That means concentration term which is used, that is number of moles of that substance upon volume of solution. That means here the total volume of solution in which the number of moles of that substance present in it, the ratio of this is the concentration of that substance. We can write the concentration of each species at equilibrium. At equilibrium. Now equilibrium is attained in this ionic equilibrium. Therefore, there are how many moles are present at equilibrium of HA? 1 minus alpha. At equilibrium, 1 minus alpha moles of HA are there. Therefore, 1 minus alpha upon volume. Here, volume of solution is V dm cube or V liter. Therefore, in V liter solution, only 1 minus alpha moles of HA are there at equilibrium. And at equilibrium, alpha moles of H3O plus is present in V dm cube of solution. Similarly, alpha moles of A minus ions are there in V liter or V dm cube of solution, and that are the concentrations of each species at equilibrium. When equilibrium is attained, the concentration moles of HA is 1 minus alpha. When volume is divided to this, then we get the concentration of that species at equilibrium. Concentration of each species at equilibrium. Therefore, we can write the concentration of HA at equilibrium is 1 minus alpha upon V. Concentration of H plus or H3O plus ion, that is alpha upon V, and concentration of A minus ion, that is also alpha upon V. Then here now equilibrium is attained in this equation, and concentration of each term, that is concentration of HA is 1 minus alpha upon V, concentration of H3O plus is alpha upon V, and concentration of A minus is alpha upon V. Then here equilibrium is attained, that means chemical equilibrium is present in above chemical equation. Therefore, we can applying law of mass action, applying law of mass action to above equation. Therefore, we get Ka is equals to concentration of H3O plus into concentration of A minus upon concentration of HA. Then putting the value of these all. See here, concentration of HA is 1 minus alpha upon V. Concentration of H3O plus is alpha upon V. Concentration of A minus, that is alpha upon V. Therefore, see here, the equation now becomes, that is Ka is equals to alpha upon V into alpha upon V. Concentration of H3O plus is alpha upon V. Concentration of A minus alpha upon V. Therefore, upon concentration of HA is 1 minus alpha upon V. Then reversing the equation. Therefore, we get alpha square upon V square. Alpha into alpha, alpha square. V into V, V square. On reversing this equation, V upon 1 minus alpha. Therefore, Ka is equals to, here V square, that means V into V, get cancelled, and we get alpha square upon V into 1 minus alpha. Then see here, suppose alpha is very small. Why alpha is very small? Because alpha is very small. That means here alpha is the degree of dissociation of weak electrolyte. H is a weak acid. It is very weak. Therefore, very less amount, less moles undergoes dissociation. Then alpha is the degree of dissociation. Very few moles of weak acid undergoes dissociation. Therefore, alpha is the degree of dissociation. Therefore, alpha is very small. That means here 1 minus alpha is nearly becomes equals to 1. That means alpha is so small. That means we can subtract alpha from 1. Then becomes the value. It nearly becomes 1. Therefore, we can rearrange the equation, that is Ka is equals to alpha square upon here V into 1 minus alpha is nearly equals to 1. 1 minus alpha is nearly equals to 1 because alpha value is very less. Then very less value when subtracted from 1, then the value which is obtained is nearly equals to 1. Therefore, here equation becomes Ka is equals to alpha square upon V. Then rearranging this equation, that is alpha square is equals to Ka into V. Then see here, alpha is equals to alpha square, that is taking square root on both sides. Therefore, square root of Ka into V. Then Ka is a dissociation constant. When E is equals to sign is removed, then constant should be removed. And therefore, alpha is directly proportional to square root of V. But we know that V is nothing but it is a 1 upon C. Therefore, this equation alpha is directly proportional to the square root of 1 upon C, because V is equals to 1 upon C. That means volume is depends upon the concentration and it is a reciprocal of concentration. Therefore, alpha means degree of dissociation is proportional to the 1 upon root C, or alpha is inversely proportional to the square root of its concentration. That is the Oswald dilution law for weak acid. Then what is Oswald dilution law for weak acid? Then see here, alpha is the degree of dissociation of that weak acid. Then it is a relationship between degree of dissociation and dissociation constant of that weak acid. Then according to Oswald dilution law, degree of dissociation of weak acid is directly proportional to the square root of its volume. Volume means dilution. That means degree of dissociation of weak acid is directly proportional to the square root of its dilution, or degree of dissociation of weak acid is inversely proportional to the square root of its concentration. That is the Oswald's dilution law for weak acid. Similarly, we can derive the same equation for weak base, which can express quantitative concentration of the weak base. Then instead of HA, if we have taken BOH, it dissociates to gives B plus OH minus ion, and here also 1 mole of BOH, 1 mole of BOH, that is weak base dissolved in VDM cube of solution. At equilibrium, alpha moles of weak base undergoes dissociated. Therefore, here we can write the derivation for weak base. We will discussing on the Ostwald's law for weak base. Then it is also, then see here, Oswald Dilution Law for weak base. It is also expression. It is also derivation which indicates relationship between dissociation constant of weak base, that is Kb, and alpha, that is degree of dissociation of weak base. Then see here, the weak base BOH in aqueous medium, it dissociates feebly. That means in small extent, very small extent, it undergoes dissociation. That means very small, very less moles of weak base undergoes dissociation to gives B plus OH minus ion in aqueous medium. Here at initial 1 mole of BOH, that is weak base, dissolved in VDM cube of, or V liter. VDM cube means V liter solution. Then at start, when 1 mole of BOH dissolved in VDM cube of solution, then here B plus ion and OH minus ions are absent. As reaction started, out of that 1 mole, only alpha moles, that is alpha moles undergoes dissociated. Alpha moles, that is very less number of moles undergoes dissociation, and therefore at equilibrium alpha moles undergoes dissociated of weak base. Therefore here alpha moles of B plus and alpha moles of OH minus ions are obtained at equilibrium. Here therefore at equilibrium the number of moles of weak base BOH is 1 minus alpha. Out of 1 mole, alpha moles undergoes dissociation. Therefore 1 minus alpha moles remains in the solution at equilibrium, and alpha moles of B plus and alpha moles of OH minus ions are formed here. Therefore we can calculate the concentration at equilibrium of each species. Then see here, at equilibrium 1 minus alpha moles of BOH is there. 1 minus alpha moles are present at equilibrium in V dm cube of solution. Therefore, concentration of BOH is, that is concentration of BOH is equals to 1 minus alpha upon V. Similarly, we can write the concentration of B plus at equilibrium. At equilibrium, alpha moles are there in V dm cube of solution. Similarly, OH minus ions, the number of OH minus ions are alpha. Therefore, concentration of OH minus ion is alpha upon V. Therefore, we can write the concentration of B plus is equals to alpha upon V, and concentration of OH minus ion is also alpha upon V. Therefore, applying law of mass action to above equilibria, ionic equilibria. When we apply law of mass action to this ionic equilibria, then we can get Kb. Why Kb here? Because weak base dissolved in aqueous medium. Therefore, here dissociation constant of base is obtained. Kb is equals to concentration of B plus into concentration of OH minus ion upon concentration of BOH. Then putting the value of concentration at equilibrium. At equilibrium, concentration of BOH is 1 minus alpha upon V, and concentration of B plus and OH minus ion is the same, that is alpha upon V. Therefore, alpha upon V into alpha upon V upon 1 minus alpha upon V. Then reversing equation. Therefore, we get Kb is equals to alpha square upon V square into V upon 1 minus alpha. Therefore, Kb is equals to alpha square upon V get cancelled. Therefore, V into 1 minus alpha. But here alpha is very small. Very small, because here base is weak base, and therefore out of 1 mole, very less moles of that weak base undergoes dissociation. Therefore, here as the value of alpha is very less, therefore 1 minus alpha is nearly equals to 1. Therefore, this equation becomes Kb is equals to alpha square upon phi into 1, that means alpha square upon phi. Therefore, rearranging this equation, alpha is equals to square root of Kb into phi, and therefore alpha, that is degree of dissociation, is directly proportional to the square root of its dilution, or phi is nothing but it is a reciprocal of concentration. Therefore, alpha, that means degree of dissociation, is inversely proportional to the concentration of C. Then see here, the same equation for weak base is also obtained, is similar like the equation of Oswald Dilution Law for weak acid. That is the Oswald Dilution Law for weak acid as well as weak base. That means here degree of dissociation of weak base is directly proportional to the square root of its volume, that is square root of its dilution, and degree of dissociation is inversely proportional to the square root of its concentration. That is about the Oswald's dilution law for weak base and weak acid, and which gives the relationship between degree of dissociation and dissociation constant of weak electrolyte. Thank you.